In this video, we're going to be solving dynamics problems in AP Physics 1. An applied 25 Newton force pushes down at 20 degrees below horizontal on a 5 kilogram box resting on a frictionless horizontal surface. Determine the applied forces Fx and Fy components. So first we resolve this force that is at an angle into x and y components. Since the angle is measured from the horizontal, we can represent f of x here, and we can represent f of y here. So f of x is going to equal to the force times cosine of the angle, which is 20 degrees. And f of y is going to equal to f times sine of the angle, which is going to be f sine of 20 degrees. Now this is going to equal to 23.5 newtons to the right. And this is going to equal to 8.55 newtons to the downward direction. What is the normal force that is acting on the block? So normal force is the force that is perpendicular to the surface of contact. This is the surface that we are measuring this block from, so this is Fn. This force is going to be equal to the force that is acting downwards as well. This is going to be the weight force of the blocks, which is equal to the mass of the block times the gravity. So our weight is going to be equal to mg, which is equal to the normal force. So we can find weight using dimensional analysis. We can plug in our mass, and we can plug in the gravitational constant. So this will result in 49 kilograms times meters over second squared, which is the same as 49 newtons. Now we have to include the downward applied component. Downward applied component. Downward, we have weight, which is equal to 49 newtons. And then we have vertically, we have our 8.6 newtons, which we're going to add together. So that's going to be 57.6 newtons. And we know that the vertical acceleration is going to equal to 0 because it's not going through the surface. So that means that you can write the normal force minus 57.6 is equal to 0. Therefore, the normal force is equal to 57.6 newtons up. Draw a complete force diagram for the block with numbers and labels. On the block, you have the normal force. This normal force is actually going to be larger than the weight. Now your weight, you're going to have 49 newtons down. And our applied vertical is going to be equal to 8.6 newtons. Our applied horizontal, you can say F. We can actually label this FAY and FAX, which is 23 newtons. This is FA. Now, on the left, we have nothing because it is frictionless. Now, your largest arrow is going to be this 58 newtons. In order to find the magnitude and direction of the block, we have to remember that only the horizontal force causes motion. Horizontal is equal to your motion. That's your only contributing factor because your vertical cancels out. So F net x is equal to 23 newtons. Using F is equal to mass times acceleration, you can use the rearranged form A over Fm. Plugging in, you have 23 newtons. over 5.0 kilograms. Since we know that 1 Newton is equal to 1 kilogram times meters over second squared, we know that the units cancel, so our acceleration is going to equal to 23 kilograms times meters over second squared divided by 5.0 kilograms. We see that our kilograms, it cancels out. And then we're left with 4.6 meters per second squared, and this is to the right. How long will it take to move a meter? Using kinematics, we know that x, your displacement, is equal to 1/2 acceleration times your time squared. Given that x is going to be 1.0 meters and a is going to be equal to 4.6 meters squared, we can write 1.0 is equal to 1/2 4.6 t squared. 1.0, 2.3 t squared is equal to 1.0 over 2.3, which is going to be 0.435. Taking the root of both sides, we have that t is equal to 0.66 seconds. A 710 kilogram car uniformly accelerates from rest and travels 40 meters in 3 seconds. What is the acceleration of the car and what is the net force on the car? So, given that our mass is 710 kilograms, given that x is equal to 40 meters, 40.0 meters, and t is equal to 3.0 seconds, we also know that it starts from rest, so our initial is equal to 0. We can use our kinematics formula. X is equal to 1/2 a t squared, which is going to be 40.0 is equal to 1/2 a times 3.0 squared, which is equal to 1/2 a times 9. So this is equal to 4.5. A, 40.0. A is going to equal to 40.0 divided by 4.5. A is going to equal to 8.89 meters per second squared. Now, suppose the car is traveling at 25 meters per second. Its brakes can apply a force of 5,000 newtons. What is the braking acceleration of the car and the time to stop? So, we know that above we also have to find what the net force is. So F is equal to MA. Plugging in, we have F is equal to 710 kilograms times 8.89 meters per second squared. This is going to be 6,310 kilograms times meters per second squared, which is equal to 6,310 newtons, which is approximately 6,300 newtons. For this question, we know that the force is equal to 5,000 newtons. Your mass is going to be equal to 710 kilograms. A is equal to F over M. Plugging in, that's negative 5,000 newtons divided by 710 kilograms. That's equal to negative 7.04 meters per second squared. What is the minimum distance required for the car to stop? So we know that V is equal to V initial plus your acceleration times time. So 0 is equal to 25 plus negative 7 times t. Negative 25 is equal to negative 7t. T is equal to 3.57 seconds. So this is approximately 3.5 seconds. During a head-on collision, passengers in the front seat of a car accelerate from 13.3 meters per second to rest in 10 seconds. What is the acceleration of the passengers? So we have that V initial is equal to 13.3 meters per second. We have that V final is equal to 0, and we have that the time is equal to 0.10 seconds. So for acceleration, we know that A is equal to the final velocity minus the initial velocity over t. Same thing as the delta V over the t time interval. So that is going to be 0 minus 13.3 divided by 0.10, which was our time interval. This is equal to negative 133 meters per second squared. And this is approximately 130 meters per second squared. What force must a seatbelt exert to keep a 25-kilogram child from hitting the dashboard? So, using F is equal to ma, we know that this will just be 25 kilograms times negative 133 meters per second squared, which is just equal to negative 3,325 newtons, which is equal to approximately 3,300 newtons. What is the effective g-force? The g-force of a child can be measured with g is equal to a over g. We know that our acceleration, a, was 130 meters per second squared, divided by 9.8 meters per second squared. So this is just going to equal to 13 g's, because that meters per second squared unit, it cancels out. A 3,500 kilogram helicopter accelerates upward at 1.2 meters per second squared. What lift force is exerted by the air on the propellers? So given that the mass is equal to 3,500 kilograms and our acceleration upward is equal to 1.2 meters per second squared, and our g, gravitational constant, is 9.8 meters per second squared, we can first draw the FBD. So for the FBD, we have our lift force, which is up, our FA, which is our lift up, which is unknown right now. And we also have our weight, which is equal to mg. Since we know that the acceleration is in the upward direction, we know that net force is going to be up. So after this, we have to write our Newton's second law. So Newton's second law states that the summation of Fy is equal to ma. So if we determine that our upwards is positive, setting our coordinate axes, then we can write that the lift, which is in the positive direction, minus the mass times gravity, which is our weight, which is in the downward direction, is equal to the ma of the system. So L is equal to ma plus mg. So L is equal to m times a plus g, if you factor out the m. After this, you can plug in with units. So we're going to have 3,500 kilograms times 1.2 meters per second squared plus 9.8 meters per second squared. That's going to equal to 3,500 kilograms times 11.0 meters per second squared. Now, if you multiply this, you're going to have 38,500 kilograms times meters per second squared. That unit is just equal to newtons. So that's going to be 38,500 newtons up. Now, we also want the magnitudes of the FBD. So we know that the weight is going to be equal to 3,500 times 9.8. That is equal to 34,300 newtons. So therefore, we know that the lift arrow is going to be longer than the weight arrow. F of our lift, let's just call this our lift, is going to be greater than our weight because it's accelerating upwards. It makes sense because our upward force has to be greater than our downward force. A 1 kilogram block A rests on a table. A cord attached to the block extends horizontally to a pulley at the edge of the table. A 0.5 kilogram mass B hangs at the end of the cord. Block A can exert a 1.5 Newton max friction force against the motion. What is the net force on the blocks? So we're given that the mass of A is 1.0 kilograms. We're given that the mass of B is 0.50 kilograms. We know that our max friction, F max, is going to be 1.5 newtons, and we also know our G is 9.8 meters per second squared. So first, we're going to compute the weight of hanging mass B. WB is going to equal to 0.50 kilograms times 9.8 meters per second squared. WB will equal to 4.9 newtons using the units of kilograms times meters per second squared. Now we have to determine the net force of the system. So we know that our driving force is equal to the weight of B, and we know that our opposing motion is equal to the friction on A. So then we can write that F net is equal to 4.9 newtons minus 1.5 newtons, and that is equal to 3.4 newtons to the right. If we define our positive as right and our negative as down, and our positive as right, our negative as left, and our positive y as up, calculate the value of the acceleration of block A and B of the system. Remember, the force moves all of the mass. So, in order to calculate the acceleration on the system, we know that m total is going to be all of the mass. That's going to be 1 plus 0.50. Now, that is 1.5 kilograms. Now, we can use our net. So A is going to equal to F net of the system divided by the mass of the system. This is going to equal to 3.4 newtons divided by 1.5 kilograms. Now, we know that 1 newton is equal to 1 kilogram times meters per second squared. So A is actually going to equal to 3.4 kilograms times meters per second squared. Dividing this by 1.5 kilograms, we have that A is equal to 2.27 meters per second squared, which is correct for the units of acceleration. And this is approximately 2.3 meters per second squared. Calculate the tension in the cord. The tension comes from the force on what it is towed. So this is our tension. So we have to use block A. And this is going to be horizontal, as you can see. The tension force is going in this direction. This tension force and this tension force are going to be the same because it's one string. One tension. So, the tension, if we define our coordinate system like this. Up is positive and right is positive. So T minus the force of friction is equal to the mass of A times your acceleration. T minus 1.5 is equal to 1.0 times 2.3. This is equal to 2.3. T is equal to 3.8 newtons. Clearly draw and label and put numbers on force vectors acting on each object. So we're going to draw the FBDs. On block A, we have our normal force, which is going to be up. Fn is going to be equal to 9.8 newtons. Now, downward, we have our weight, which is going to equal to 9.8 newtons. On the right, we have our tension force, Ft, which is going to equal to 3.8 newtons. And to the left, we have our friction force. Which is going to be equal to 1.5 newtons, Ff. Now, our largest arrow is going to be our largest horizontal arrow is going to be 3.8 newtons. Let's make this a little longer. And now for block B, we only have two forces. We first have our tension force, which is Ft, which is equal to the same 3.8 newtons since this is one tension string. And then downwards, we have our weight. Our weight is equal to 4.9 newtons. Now, this is equal to the mass of this times the gravity. This is also mass times gravity, which is how we got that. And these two are the same. Our Fn and our weight are the same since there is no vertical acceleration for block A. And our and our weight is the only downward force on our block B. There is no normal force on block B because it is not on a surface, it's in the air. So it's not in contact with a horizontal axis that is supporting it upwards. This is a picture of an Atwood machine. Two masses attached by a string to a frictionless massless pulley. The mass of block A is 0.5 kilograms and the mass of B is 0.2 kilograms. What is the system's acceleration when the blocks are released? So we're given that the mass of A is equal to 0.50 kilograms. And we're given the mass of B is equal to 0.20 kilograms. We know that the one that is heavier will go down. So, in order to find the acceleration, for Atwood machines, the acceleration is equal to the mass of A minus the mass of B times the gravity, divided by the mass of A plus the mass of B. If we plug in, we have 0.50 minus 0.20 kilograms times 9.8 meters per second squared, divided by 0.70 kilograms. This is going to equal to 4.2 meters per second squared, which is approximately 4.1 meters per second squared. How long will it take for block A to fall 2 meters? We had kilograms cancel here. We know that x, our displacement, is equal to 1/2 at squared. Our displacement we want to find is 2.0, 1/2. Our 4.1 is our acceleration, and our t squared is our unknown. So 2.0 is equal to 2.05 t squared. T squared is going to equal to 2.0 divided by 2.05. T squared is going to equal to 0.976, and this is approximately 0.99 seconds, approximately 1 second. After you take the root, 0.976 t squared. Now, after this, because block A's larger mass moves the system, does this mean that A exerts more force on mass B than mass B exerts on mass A via the string? Explain. The answer is no. This is because the tension is the same on both sides. The reason for this is because it is one string. So we can use Newton's third law. Force A exerts the magnitude of force A that it exerts on the string is equal to the force the string exerts on A. Force B exerts a magnitude of force onto the string, and that's going to equal to the force the string exerts on B. They're going to have equal magnitude. And then the reason why they accelerate differently is because their masses differ. Not because their forces differ. So when you have force is equal to mass times acceleration, it is dependent on both mass, acceleration, and it's dependent on force, mass, and acceleration. So it does, just because they have different accelerations, it doesn't mean that it's solely because of force. Mass is also a key player in the acceleration. Pertaining to question 6, we can derive the equation for acceleration by starting off with the weight of A is equal to the mass of A times the gravity. Let's define the forces that are on block A. So it also has the force of tension, which is up. This is down. So then if we use Newton's second law, F is equal to ma. This will be mag minus t is equal to mass of A times acceleration. This is your first equation. Now, for block B, this is going to be moving, this A is going to be moving down and B is going to be moving up. So T is going to be acting up, and the weight of B is equal to mb. G is going to be acting down. So it accelerates upward. So we can take upward as positive for B. So for block B, this is going to be positive. And for block A, this is going to be positive. So we can write the Newton's second law for block B. Our second equation is going to be the tension minus mbg is equal to mba. Now we have two equations. So we can eliminate the tension by adding the equations together. So we're going to have mag minus t is equal to maa. And we're going to have t minus mbg is equal to mba. So on the left, we're going to have and then we see that our tensions cancel. On the right, we're going to have MA plus MBA. If we factor here, we have MA plus MB. Actually, I'll highlight A is equal to times A is equal to mag minus mbg. Now that you have this equality, you can solve for acceleration, which is this formula up here.